You really can't help but notice it lately. Seems like every other week there's a story about really major flooding somewhere in the world.
It does feel more frequent, yeah.
Yeah, like torrential rains just swamping cities or rivers just completely overflowing. And the impact, I mean, it's just devastating for people, for the economy, for the environment.
Absolutely. It really underlines how critical it is that we get better at predicting these things,
Yeah.
when and where they'll hit, so people can actually prepare.
Exactly. Reduce the damage, hopefully.
Huh.
But keeping up with all the info on this stuff, honestly, it feels like its own flood of data sometimes.
Right.
So in this deep dive, we want to, cut through some of that noise.
That's the plan. And today, we're looking at something really quite interesting, a new approach to flood forecasting. It's called HydrographNet.
HydrographNet. Okay.
Yeah, it comes from some research detailed in a 2025 paper. It was in computer-aided civil engineering, Tagazida and others. What's really promising about it is how it blends machine learning, computers learning from data, with fundamental physics.
Ah, okay. So not just data, but the actual rules of how water behaves.
Precisely. The goal is to get predictions that are more accurate, sure, but also, and this is key, more understandable, more interpretable. The sources you sent over really show how complex flood modeling is, and this HydrographNet,
Mm-hmm.
well, it looks like it could be a real step forward.
Yeah, it sounds like it. And for listeners, I think what's really compelling here is, well, think about traditional flood models. They can be super detailed, incredibly accurate sometimes, but they often need massive computing power.
Right. Huge amounts. And time.
Exactly. Not ideal if you need a forecast now or if you're trying to assess risk over a really big area.
Mm.
But then the earlier machine learning attempts, well, they were faster maybe, but sometimes they felt like a black box. You got an answer, but you didn't know why. And sometimes, they'd predict things that just didn't make physical sense.
Like water flowing uphill.
Yeah.
Not ideal.
Yeah. Not ideal at all. So HydrographNet seems to be aiming right at that sweet spot, trying to tackle both problems, faster predictions, but predictions that are still, grounded in reality. And get this, the results they're showing. Some really surprising accuracy gains, plus this fascinating way the model seems to almost understand the landscape. Okay, so let's get into the nitty-gritty. Why is it so hard to get reliable flood forecasts anyway?
That's a great place to start. It really boils down to a few main things. First, you've got different types of floods. There's pluvial flooding, that's basically heavy rain, overwhelming drainage, often in cities.
Right, the flash floods.
Yeah. And then fluvial floods, which is when rivers actually overflow their banks. And sometimes these can happen together, or one can trigger the other, making it even more complex.
Okay, so multiple causes potentially interacting.
Exactly. Then, like you said, the purely data-driven models,
Hmm.
they can be efficient, but they're often these black boxes. You get a number, but no insight. And worse, they might predict something physically impossible. You can't suddenly have more water in an area than what was there plus what flowed in, minus maybe what soaked into the ground. Basic stuff.
Basic conservation, yeah.
Right. But these models don't inherently know that. And finally, the traditional hydrodynamic models, the ones based on solving the physics equations, the shallow water equations, they are based on physics, which is good, but they are incredibly computationally intensive.
The ones that need the supercomputers.
Pretty much.
Yeah.
Running those for large areas or long forecast times can take days. Not exactly helpful for timely warnings.
Right, so it sounds like this constant tension, computing power versus physical accuracy versus speed.
That's a good way to put it.
And that's where these graph neural networks, GNNs, come in. I remember seeing that mentioned.
Exactly. GNNs are really promising here because they're designed for data that isn't nicely structured like a grid. Think about a floodplain. It's messy, right? Regular shapes, different elevations, vegetation.
Totally unstructured, yeah.
So GNNs can represent this complex area as a graph. Imagine little points or nodes scattered across the floodplain, representing different locations. And then edges or connections between those points show how they relate spatially, maybe how close they are, or if water can flow between them.
Okay, like a network map of the floodplain itself.
Precisely. And what's powerful is how they capture changes over space and time. They use something called message passing.
Message passing?
Yeah, think of each point talking to its neighbors,
Okay.
sharing info about, say, its current water level, its elevation, things like that. This lets the model understand how conditions in one spot affect the surrounding areas and how that changes over time. It's a natural fit for modeling how floodwaters move across these complex terrains.
Okay, that makes sense. Points talking to each other, sharing flood info. So Instead of forcing reality onto a grid, you build a network that matches reality. But the big leap with HydrographNet is that it's physics-informed. What does that actually mean? How does it get the physics in there?
That's the core innovation, really.
Yeah.
It takes the GNN's strength with spatial data and directly bakes in fundamental physics laws during its learning process. Specifically, mass conservation, the simple idea that water doesn't just vanish or appear out of nowhere.
Right. Can't create or destroy water.
Exactly. Now, other methods try to enforce physics too, but they often use computationally very heavy techniques, like automatic differentiation, to ensure the model follows the physics equations precisely. HydrographNet does something quite a bit cleverer and more efficient.
Okay.
It includes checks against these physical principles, like mass conservation, directly in its loss function. The loss function is basically how the model grades itself during training.
Like its report card.
Exactly. So by putting physics checks on the report card, the model learns not just to match the observed flood data, but also to make predictions that are physically plausible, that obey the rules of water. And it does this without that huge computational overhead. It's basically telling the model, hey, your answers need to match the data and make physical sense.
Ah, okay. So it's like built-in physical guardrails. That sounds like it would definitely help avoid those water flowing uphill predictions.
It's designed to, yes,
Yes.
keep it grounded in reality.
Now, something else that jumped out was this mention of long-term stability and a push-forward trick. Floods aren't instant, right? They evolve over hours, days even. So predicting reliably over longer periods seems crucial. How does HydrographNet handle that?
You're spot on. Predicting floods often involves what we call autoregressive forecasting. The model uses its own previous prediction to make the next prediction, like predicting tomorrow's weather based on today's forecast, which itself was a prediction.
Okay, I see the potential problem there. Errors could build up.
Exactly. Even tiny errors early on can compound and accumulate, leading to forecasts that get worse and worse the further out you look. The push-forward trick is a technique HydrographNet uses to combat this. During training, it's not always given the perfect ground truth data from the previous step.
Oh.
Sometimes it's deliberately fed slightly noisy or slightly incorrect inputs, mimicking the kinds of small errors it might make itself when forecasting. This forces the model to learn to be more robust, to handle small inaccuracies and correct for them, stopping them from snowballing.
Ah, interesting. Like teaching it to recover from small wobbles so it doesn't veer completely off course over time.
That's a great analogy.
Yeah.
It learns to self-correct, which is vital for those longer forecasts.
Okay, that makes a lot of sense. Now, this next bit, this is where I thought it got really fascinating, especially for understanding why a flood might happen a certain way. The research mentions using Kolmogorov Arnold Network's cans for interpretability. That sounds technical. Can you break down what cans are and how they help us peek inside the model?
Absolutely.
Yeah.
CANs are a relatively new type of neural network, and they work quite differently from standard ones. Instead of using fixed numbers or weights between nodes, CANs use learnable functions.
Learnable functions.
Yeah, think of them as adaptable mathematical curves. Instead of just multiplying an input by a fixed weight, the CAN learns an entire curve that describes the relationship between, say, elevation and its impact on water depth. These curves are often built using splines, flexible, smooth lines that can bend into different shapes.
Okay.
What's so powerful about this is that HydrographNet can learn and then actually show us the specific relationships it found between different environmental factors and the flood dynamics. Things like land elevation, slope, ground roughness, what hydrologists call Manning's coefficient.
Right, how easily water flows.
Exactly. And even the shape of the terrain, its curvature. Because these relationships are learned as functions we can actually look at, we can visualize them. We can see, for instance, how the model weights different elevation ranges or how different slopes influence water movement in its mind.
Wow. Okay, so it's not just giving us a prediction like water depth will be X here. It can actually show us why, based on the landscape features it learned are important, like I'm predicting high water here because it's low-lying and concave. That seems huge for making it less of a black box.
It's a massive step for transparency, yes. For someone like an urban planner, this could mean seeing exactly which low-lying concave areas the model flags as most vulnerable based on learned principles, allowing much more targeted action than just a general flood map might offer.
That makes perfect sense. And presumably, learning these meaningful relationships also helps make the predictions themselves more physically sound.
Exactly. It reinforces the physical plausibility. If the model learns relationships that align with known hydrology, it's less likely to produce completely nonsensical outputs.
Okay, so we've got this physics-informed GNN, using cans for interpretability, and the push-forward trick for long-term stability. How does this all fit together? The paper mentioned an encoder-processor-decoder structure. What do those parts do?
All right, think of it as a data processing pipeline. First, the encoder. Its job is to gather and initially process all the input data. This includes the static stuff, things that don't change, like elevation, slope, roughness, curvature, and the dynamic stuff, things that do change, like the water levels from the previous time step.
Mm-hmm.
It also takes in broader factors, like maybe upstream river flow or recent rainfall totals, and those spatial relationships between points for the graph structure. And importantly, the cans are used right here in the encoder, specifically for processing those static terrain features.
Got it. So cans help encode the landscape understanding.
Exactly. Then comes the processor. This is really the workhorse. It's made up of several GNN layers that take the encoded information and refine it through that message. Passing, we talked about letting the points talk to each other,
Yeah.
sharing information back and forth to understand the complex spatial and temporal patterns of the flood evolving.
Okay, so that's where the complex interactions are figured out.
Right. And finally, the decoder. Its job is to take the highly refined information from the processor and translate it into the final predictions we want. Usually, the water depth and maybe the water volume at each point for future time steps.
And spits out the forecast.
Basically, yeah. And remember, it's autoregressive. The decoder's output for one time step becomes part of the input for the next time step prediction. It simulates the progression.
Encoder gathers, processor thinks, decoder predicts. Got it. Now, let's dig back into that physics-informed loss function. You said it's key for mass conservation. How exactly does it enforce that?
Okay, so the loss function has a few parts. There's the standard prediction loss. That just measures how far off the model's predictions of water depth and volume are for the actual ground truth data it was trained on. Typical machine learning stuff minimize the error.
Standard accuracy check.
Right, but then there's the crucial physics-based loss. This is where mass conservation comes in directly. The researchers derived two key rules, basically inequalities, from the fundamental continuity equation, the idea that water change equals inflow minus outflow, minus infiltration, water soaking in.
Okay, two rules.
Rule 1 basically says, the total predicted water volume across the whole area at the next time step can't be more than the volume now, plus any incoming water, rain, river flow, minus any infiltration. You can't magically create water.
Makes sense.
Rule 2 is similar, but flips it slightly. The actual observed volume at the next step shouldn't be less than what the model predicted, considering the inputs. It helps prevent the model from predicting water just disappearing unrealistically.
Okay, bounding it from both sides, essentially.
Kinda. And to make sure the model only gets punished when it actually breaks these rules, they use a function called ReLU. Think of that like. It only adds a penalty to the loss if the prediction violates one of these physical constraints. If it's plausible, ReLU does nothing.
So it only complains when the physics doesn't add up.
Exactly. And there's one more piece you mentioned, the penalty loss.
Yeah, what's that one?
That adds another layer of physical consistency. Since the model predicts both water depth and water volume in each little area or graph node, those two things need to relate logically. The penalty loss enforces the simple idea that the average depth in a cell, volume divided by area, can't be greater than the maximum depth predicted in that same cell.
Ah, right. That would be physically weird if the average was higher than the peak.
Exactly. It ensures the predicted depth and volume make sense together. Again, using ReLU, so it only penalizes violations.
Okay, that's quite a sophisticated way to weave physics in without explicitly solving those complex equations. So they tested this whole system, the White River in Indiana, right? Why there, and how did they test it?
Yeah, the White River near Muncie. It was a good test case because it gets both kinds of floods, the pluvial ones from rain and the fluvial ones when the river itself swells.
The good mix of challenges.
Right. Now, to get the data to train and test HydrographNet, they didn't just rely on past real-world flood measurements, which can be sparse. Instead, they used a widely respected traditional hydrodynamic model, HECRS.
Oh, so they used a traditional model to generate data for the AI model.
Exactly. They ran lots of HECRS simulations of the White River area, feeding it a wide variety of synthetic but realistic river flow patterns, hydrographs, and rainfall patterns, hydrographs. This created a really rich, diverse data set covering many different potential flood scenarios.
So they could train HydrographNet on how HECRS thinks floods behave there.
Precisely. And it was a decent-sized area they modeled. The computational mesh had almost 5,000 nodes, or points, so quite detailed. This variety and detail really let them push HydrographNet and see how robust it was.
Okay, makes sense. And the results, how did it actually perform? I remember you said they were impressive.
They really were quite striking. First, they compared HydrographNet to a baseline GNM Model 1 without the physics-informed loss and without the CAN layers. HydrographNet achieved a 67% reduction in prediction error.
Wow, 2/3 less error. That's huge.
It is. And maybe even more importantly, its error in terms of mass balance conserving water was practically zero. It almost perfectly respected that physical principle, while the baseline GNN did not. It had significant mass balance errors.
So the physics part really worked.
It really seemed to. Then, looking at actual flood events, like did it correctly predict areas flooding above certain depths, say 5 centimeters or 30 centimeters, HydrographNet showed a 58% improvement in something called the Critical Success Index, or CSI.
Which means?
Basically, it was much better at correctly identifying significant flooding, hitting the flooded areas, and avoiding false alarms. Much more reliable for actual warnings.
That's critical. Yeah, getting the warning right.
Absolutely. It was also much better at predicting the timing when floodwaters would actually arrive at specific locations. Again, crucial for evacuations. And finally, it did a better job capturing how the flooded area spread over time. The baseline GNN tended to overestimate how far the water would reach. HydrographNet was more accurate spatially.
Okay, so better on error, better on physics, better on detecting events, better on timing, better on spatial spread. Sounds like a clean sweep.
Pretty much across the board, yeah.
But I'm really curious about that CAN interpretability in action. What did they actually learn by looking inside the model for the White River? What did it tell them about how the landscape affects flooding there?
For someone thinking about their own property, say, knowing how the model wave slope could give a much more specific risk assessment, right?
Definitely. And this is where it gets really insightful. By visualizing those learned CAN curves for the different inputs. For elevation, the curve clearly showed the model prioritizing lower elevations much more heavily. Makes perfect sense. Water pools in low spots.
Obvious, but good the model learned it.
Exactly. For curvature, it weighted concave areas, dips and bowls in the land that hold water higher than convex areas, like ridges, which shed water. Again, perfectly matches hydrological intuition.
For Manning's roughness, the roughness of the ground, it learned a sort of U-shaped relationship. Both very smooth surfaces, which allow fast flow, and very rough surfaces, which slow water down and can cause ponding, were identified as important.
Interesting. Not just one extreme.
Right. And maybe the most fascinating was slope. The CAN showed peak importance for moderate slopes in this area. That turned out to be around 25-30 degrees. The researchers noted that these slopes often correspond to the riverbanks and the transition zones between the main channel and the floodplain.
Ah, the areas where water spills out.
Exactly. The critical interface. The fact that the model independently learned to focus on these specific hydrologically crucial landscape features gives you a lot of confidence that it's not just fitting data, it's actually capturing some understanding of the underlying processes.
That is incredible. It's like it learned basic hydrology principles just from the data and the physics constraints. And did adding the CANs actually help performance, or was it just for interpretability, just for show?
No, it definitely helped performance too. They ran comparisons HydrographNet with CANs versus a version without them, but still with the physics loss. The version with CANs consistently performed better across all the metrics. Lower error, better CSI, everything.
So CANs are doing double duty and making it interpretable and making it more accurate.
It seems so. It suggests that forcing the model to learn these interpretable, likely more physically meaningful relationships actually improves its predictive power. For that urban planner again, this means the improved accuracy is partly because the model better understands the terrain, leading to potentially more robust plans.
Okay, and the final piece? Speed. Those traditional models are slow. How does HydrographNet stack up?
That's another big win. While it's much more accurate than the baseline GNN, its inference time, how long it takes to make a forecast once trained, is very similar, very fast. We're talking like less than a quarter of a second to generate a 15-hour forecast for that whole White River Basin model.
Wow, okay, and compared to the traditional HEC-RIS?
Oh, dramatically faster. The paper mentioned HEC-RIS taking about 130 seconds for a comparable forecast run. HydrographNet, less than 0.25 seconds.
That's what, like 3 orders of magnitude faster?
Easily. It's that kind of speed up that really opens the door for real-time forecasting systems or for rapidly running many what-if scenarios for planning.
Incredible. So summing up then, HydrographNet really does seem like a significant advance. It hits that sweet spot. Accuracy, physical realism, thanks to the loss function, interpretability from the cans, and the efficiency needed for practical use. It tackles a lot of the drawbacks we talked about with older methods.
That's a great summary.
Yeah.
And that ability for the model to, in a sense, understand the terrain via cans. That feels like the real aha moment.
Yeah.
It hints we're moving beyond just prediction machines to tools that offer deeper insights into why floods happen the way they do.
Yeah, that intuitive understanding could be game-changing for decision makers, right? Emergency responders, infrastructure planners.
Absolutely. Having a better grasp of the underlying drivers, informed by the model's learned relationships, could lead to much more targeted and effective interventions. Better decisions all around.
So where does this go next? What's the future for this kind of technology?
The researchers mentioned several exciting directions. One is looking into multi-fidelity modeling. That's about using a mix of high-accuracy simulation data, like from HEC-RES, which is expensive to generate, and maybe lower accuracy but cheaper data sources to train the model more efficiently, reducing the reliance on huge amounts of that high-fidelity data.
Makes sense. Make it easier to train for new areas.
Exactly. Another is scalability, making these models work for even larger river basins, higher resolutions. That might involve using distributed GNN techniques, running the model across multiple processors or machines.
Handling bigger and more complex floods.
Right. And finally, improving generalizability. Making sure a model trained on one river basin can still perform well or be quickly adapted to a completely different one it's never seen before. This involves things like bigger, more diverse data sets, maybe transfer learning techniques, and domain adaptation methods to help it adjust to new conditions.
So making it more robust and adaptable globally, sounds like there's plenty still to explore.
Definitely. It's an active area of research.
Well, if you've been listening and this has piqued your interest, we'll definitely put a link in the show notes. The researchers have made the HydrographNet implementation and the dataset available on GitHub via the NVIDIA Physics Nemo repository. Worth checking out if you're technically inclined.
Yeah, it's great that they made it open source.
It really makes you think, doesn't it? How could this kind of enhanced understanding offered by interpretable AI like HydrographNet actually reshape how we design our cities, our infrastructure, in areas facing increasing flood risk? Feels like it could be quite transformative in the coming years. Definitely something to keep an eye on. It does leave you with a bit of optimism, perhaps, about tackling these challenges. So maybe the final thought for listeners is just that. How could this deeper understanding of flood dynamics really change our approach to living with water in the future? Something to ponder.